Okay, so it's now time for the last talk of the morning, and it's my pleasure to present Inder Kaur from the University of Glasgow, who will talk about moduli of parabolic bundles of rank 3 on elliptic curves.
Thank you. Thanks a lot to the organizers for giving me the opportunity to speak here. It's a real pleasure to be speaking at Frank's 60th. And also, it's a really good choice of location. I love being back at IMPA, love being back in Brazil. Lots of good memories from here. So yeah, it's fantastic to be back. OK, so also I will be talking about work that is related to the work of some people in the audience. So that's very good. So just as a starter, I'm going to give a lot of definitions, OK? But I understand that this is quite heavy notation. So whenever possible, I'm going to try to give examples in actual small rank or something so that we get used to it. But just for starters, I will define things a little bit generally. So suppose we have X to be a smooth curve. OK? So no genus specified here right now. I take a fixed set of points, P1 to PS. OK, distinct points. I presume everybody knows what is a vector bundle, but may or may not have heard of a parabolic vector bundle. So a parabolic vector bundle of rank n at P1 to PS points is a vector bundle on X of, so first of all, it's a vector bundle in its own right. But then again, what you have additionally is a quasi-parabolic structure. OK, so what is a quasi-parabolic structure? This is a flag. So on each of these points that I specified, P1, P2, P3, so on, I can look at the fiber of the vector bundle on that point. I have that as EPI, yes? And then this is a vector space. Inside this vector space, I have a filtration. Okay, I have a filtration of subvector spaces. So this is flag. So what I do is that I have at EPI is, let's say, F1. Then inside that, I have F2, and then I have F3, and so on up until Fn. OK, so these are just subspaces of the vector space. So that is a quasi-parabolic structure, what I had defined earlier. But now what I have is that I also try to, what I call by a parabolic structure is that I have these, I take a tuple in Rn, OK? Mu I, which are the weights that I attach to these vector spaces. Okay? So again, there are lots of questions you can ask here, and I will try to answer some in a bit. What you can also do is ask whether you really, let's say, if you take a vector bundle of, let's say, rank 4, and you have, let's say, 2 parabolic points or something. At one of the parabolic points, you have this by having a parabolic structure, you mean that you have this filtration, yes? But you need not always have, let's say, a threefold and then a plane and then a line, yes? You could skip a few things. So the flag need not always be complete. But in my setup, the flag will always be complete, okay? So for the sake of completion, I did state this thing about multiplicities, which is when the flag is not complete. But for our intent and purposes, we can forget about it, okay? So hopefully, so far, everything is good. People understand. I have a vector bundle, as usual, but now I have these parabolic points. I take the fiber at these points. I have a filtration by vector spaces. And to these vector spaces, I'm attaching weights. OK, so hopefully, this is comfortable in spite of there being some notation. And then you can ask, what do I mean by a subbundle? Yes? So a subbundle of a parabolic bundle is that, again, I take, first of all, a subbundle of the vector bundle in its own right, okay? And I take a filtration for the subbundle. So at each of these parabolic points, just as you would kind of imagine, yes? So how do I define this? I define it as, I look at the intersection of the fiber of the vector of the subbundle with the flag of the bundle. Okay. And then again, I have to be careful about what do I mean by parabolic weights for this subbundle. Okay. So for the subbundle, I have to always make sure that the weights that I choose, yes, this is going to be a subset of the weights that I have for the ambient bundle, but not all of them. It depends on the intersection. Okay, so I look at just the max of the weights for each part of the filtration. Okay, so this will hopefully become more clear once we start doing a little bit of examples. But essentially, what I'm trying to stress here is that it's the parabolic bundle is really, you have your bundle as usual, and then you have this flag, and you have this weights. And this is very important, because this is what determines parabolic degree. Okay, so usually what you mean by degree of a vector bundle is just you take your degree of the, I mean, you take the degree of its determinant line bundle, and that's it. But here what you have is parabolic degree, so you really need to also take into account the weights, the sum of the weights, okay? And the slope of the bundle is defined as parabolic degree over rank. Okay, so why do we go through all this weight business? Essentially to be able to define some sort of stability condition. Okay, so if you're used to moduli spaces of usual vector bundles, you know that you have stability condition coming from this degree over rank, the slope stability. But now here you have this extra parabolic structure, and again you want to have some kind of a moduli space of parabolic bundles, so you have these weights to give you parabolic degree, which is different, and then again you define stability in this way, that you say that a bundle is parabolic stable if for every parabolic subbundle I have that the parabolic degree of the subbundle over its rank, so the parabolic slope of the subbundle is strictly less than. Okay? That's when it is stable. If it is less than or equal to, it is semi-stable, just as you have for the normal stability. Okay. And then you can just basically rewrite this, right? You can rewrite this as thinking of this as mu of power e, yes, minus mu of power f being greater than or equal to 0 if something is semi-stable. And that is sometimes more helpful. It's just, you know, rewriting the equation. Okay? Okay, and as I said, for semi-stability, you have less than or equal to, and for stability, strictly less than. Okay, so this is quite a bit of definition, but hopefully it's, you know, for people who don't know it, haven't seen it ever before, this is giving some idea of what's going on. So the weights are called generic. So in usual moduli spaces of vector bundles, if you asked for the rank and degree to be co-prime, then stability and semi-stability are the same, yes? And you have something which is the moduli space is smooth. Here what you have, you say that the weights are generic, again, if semi-stability and stability coincide. And for those kinds of weights, you again have something which is smooth. Okay? So the moduli space of parabolic, semi-stable parabolic bundles was constructed by Mehta and Seshadri, and we have a dimension, I mean, this is in general, for any set of weights, this is a normal projective variety, okay, of this dimension, so taking into account the parabolic points and the weights, etc. And if the weights are generic, it is actually smooth. Okay. So I went through a few notations and definitions, but I hope everything is clear. We all have an idea of what's going on with this parabolic bundles, and that we can have a moduli space of parabolic bundles. Okay. So here's the question. Can I get back the curve from the moduli space of parabolic bundles? Okay, so asking a little bit like if I can get the cow back from the hamburger. But actually in mathematics you can. So what I mean by that is that these kind of questions are called Torelli type questions. And the motivation is from the classical Torelli, which tells you that if you take a smooth projective curve, then it is determined up to isomorphism by its principally polarized Jacobian. And what is a principally polarized Jacobian? Forget about the principal polarization part for now, but what you mean by the Jacobian, as always, is the degree 0 line bundles. So that's already a moduli space. So you do have, you know, Torelli started this question of, we have the moduli space of, let's say, rank 1, degree 0 line bundles, and actually you can retrieve the curve from that. Then people started asking whether the same can be said in higher rank. Yes, why just rank 1? And the question that I'm asking right now is whether we could also do something like this for parabolic bundles. Yes? And in the case of parabolic bundles, what I'm saying is that if, let's say, mu, these two moduli spaces are the same, then of course x is isomorphic to x prime. That's what I want. And that s goes to s prime. Yes? The set of parabolic points goes to the set of parabolic points. OK. So let's do a little bit of history. How do you normally prove things like this? How do you prove Torelli type questions? First of all, what do we know for higher rank Torelli for vector bundles, for parabolic vector bundles? So suppose I take x to be a smooth projective curve of genus G greater than or equal to 2, then Mumford and Newstead showed that actually it's not just that you can get back the curve from rank 1 degree 0 line bundles, but you can actually also get it from rank 2 vector bundles with odd degree determinant, yeah, so that it is smooth. You can also do that. And then a generalization of this was given by Narasimhan and Ramanan and Churin. So you can actually get back the curve from the moduli space of rank n odd degree or co-prime degree determinant. So always, yeah, for vector bundles, you're able to do this. And what are the methods used? Hoche theory. Okay, so I will talk a little bit about this depending on how much time I have. So just to be clear, I have 50 minutes, right, George?
Yes.
Okay, I'll try to stay within the time. But okay, so we are all, I hope, happy with what the question is, and that Mumford Newstead answered this for vector bundles. But what about parabolic vector bundles? Because as the title of my talk suggested, or maybe the abstract suggested, I'm more interested in parabolic bundles right now. So for moduli space of parabolic bundles, we have higher rank Torellis. For genus G greater than or equal to 2, this was proven by Biswas, Balaji, and Delbano Rolin in 2001, but only for rank 2 and certain weights. Yes? So in the case of moduli space of parabolic bundles, you don't just have the bundles, but you also have these weights in order to give the stability. So you also have to ask the question whether this is possible for all weights. And their results showed that it was true for certain weights. Okay. And then the case of arbitrary weights, arbitrary rank, arbitrary number of points. Yes? This was settled by Alfaya and Gomez in 2019. So this was part of Alfaya's PhD thesis. But only for genus, or the only cases remaining were genus lower than 3. Yeah, so this is quite a nice result. So this shows it for any rank, any set of weights, any number of points. And so it more or less settles the question. But the genus 0, 1, and 2 is harder, okay? Although we do have some cases there as well. For these cases, normally, for these genus, the results that we have are in rank 2 or less, so 1 or 2, yeah? And this is, and certain weights. And this is the topic of what I'm going to be discussing more. So if I take G to be the genus, R to be the rank, S to be the set of parabolic points, Biswas, Hola, Kumar, they showed it for genus 0. If I take, let's say, the number of points being greater than or equal to 5, but I need the weight to be half, half, half. Yeah, so for a very fixed weight. Okay, and then Thiago is here. So Thiago and Luana showed this for the case of elliptic curve, G equals 1. The number of points being greater than or equal to 3, and again, rank to be equal to 2, and again, for a set of weights, for a very specific weights. Yeah? Okay. Then Fernandez Vargas, Nestor Fernandez Vargas was a PhD student of Frank Loray, and he showed it in his PhD thesis, or part of his PhD thesis, that for genus 1, for just 2 points, same weights at both points. So this is not saying that the weights need to be half, half, half. No, but they need to be whatever they are. They need to be same at both the points. rank 2, and trivial determinant. Okay. So in particular, to summarize, the case of genus G equals to 1, the rank being greater than or equal to 3, arbitrary weights, arbitrary number of points is open. Yeah? And the goal of our project with Roberto Alvarenga, me, Frank, and Roberto, is to say something for the case of genus G, rank 3, and let's start with 1 point. Yeah? So this is one of the open cases. So supposing I have that P is a unique parabolic point, what does a parabolic bundle of rank 3 look like? So this is going to give me a filtration here. So I'm going to have, so I'm going to be in the case mainly with just 1 point. So it's very simple. Forget about all the i's and j's and whatnot. So I have that I have at that 1 point I have the choice of a plane and the choice of a line, yes, and a point. So a sequence of real numbers then is attached to this one, and this is in my case just going to be mu1, mu2, mu3, yes, because I only have rank 3 and I have exactly 1 point. So much simpler, and my goal is to retrieve the curve from the moduli space. So I know that the moduli space exists via Mehta and Seshadri. I just want to see if I can actually retrieve this. Okay. So I gave a lot of notations and definitions, and now I'm going to talk a little bit about the methods that are normally used. So the question you might ask when I, oh no, I'm sorry. Okay, so the question you could ask is that why was it that these results, you know, people normally when they want to do something, they want to do it as generally as possible. So why is it that these results are really limited to rank equals 2? What is the method being used and what is the limitation of the method? Yeah? So for the next part, I want to talk about what is the method that's being used in these results and why it doesn't work in some form for rank 3, and what else would you do? Okay? So again, I have to give a few definitions, but hopefully it's not too bad. So a Higgs bundle is a pair E theta consisting of a holomorphic vector bundle E, just as before, but also an element called Higgs field in the sections of NE tensor kx, where kx is the canonical bundle. And I can think of this, which is what people do. Sorry, there should be a tensor here. I can just think of this as a homomorphism from E to E tensor, the canonical bundle. Yeah? And I say that a Higgs bundle is semi-stable if for all proper subbundles, I have again that the slope of the bundle of any subbundle is less than the slope of E. But here, unlike in just the normal vector bundle case, I have to take into account the Higgs field. So these are the ones that are Higgs field invariant. Yeah? So I need that theta f is contained in here. So for all such bundles, I would need this, this condition to be satisfied. Okay. And then Hitchin and Nitsure showed that the set of, so Hitchin for rank 2 and Nitsure in general rank, that the set of all isomorphism classes of stable, and if you're taking semi-stable, then S equivalence classes of Higgs bundles forms a moduli space. Yes, and we will denote this by M Higgs. So it has dimension this, I think in the case for rank 2, but in general, maybe a bit more complicated than what I've given there. Okay, so the point is, when you look at this first time, you think, what is going on? How did they just come up with this Higgs field? We had a vector bundle, and now we have this Higgs field and this Higgs bundle, and I don't know. It seems a little bit unnatural, okay? But the thing to remember is that it's not quite so natural once you've seen this construction. So you start off with saying that, okay, suppose I have my moduli space of stable vector bundles of rank R and degree D. This is the one that I'm used to, yes, and I like. Then I take a point in this moduli space, okay, and the tangent space at that point is H1, okay, and if I apply Serre duality, what I get that cotangent space. And this is exactly the thing where every time I'm talking about Higgs field, I'm just saying I have my field, I have my vector bundle E and an element in here. Yes? Okay, so this is how the Higgs field is coming. And the characteristic polynomial is of this form, okay? And here the A1, A2, so if you want, you can think of the Higgs field as just being a matrix in one forms, yes? And then I can take the characteristic polynomial of this matrix. It's going to have coefficients. The coefficients are going to be this A1, A2, so on up until AR. This I can think of as A naught. And what I can do is that I can have a map called the Hitchin map going from the cotangent space, okay, to this sum of these sections, okay, which basically just takes E, theta. So, you know, I have already understood how I got this, yes, the theta here. And what I do is that I look at the characteristic polynomial of theta, and I look at its coefficients, and I get this, okay. Now, the cotangent space is an open subvariety of the moduli space of Higgs bundles. Okay, so of course, I'm not proving any of these results. I'm just stating them, but hopefully it's a little bit clear that these things are not as artificial as they might look the first time you see them. So this was for the case of vector bundles, yes? You can also do something similar for parabolic bundles. So a parabolic Higgs bundle is a parabolic bundle E with a Higgs field, or I should say maybe parabolic Higgs field. So this parabolic Higgs bundle, this parabolic Higgs field is basically what it does is that again I have this homomorphism from E to E tensor Ks. So here again this is my canonical bundle, but canonical bundle twisted with the divisor S. Yes, the S being the P1 to P2 PS. Okay, and what this parabolic Higgs field does is that it's supposed to take the part of the filtration, let's say EPI, and shift it to EPI plus 1. Okay, so that's what the map should do, because I have a filtration here at the parabolic points, and the image of that filtration should just be shifted by 1. Okay, so there is a name for when this happens. This is called strongly parabolic Higgs field, but I didn't want to add more things. So if it doesn't shift by 1 but just remains the same, then it's just a parabolic Higgs field. But okay, so for our purposes, this is normally what people look at. Okay, so again, the moduli space of semi-stable parabolic Higgs bundles of any rank degree and parabolic weights mu. This is actually a moduli space, and it was constructed by Yokogawa. Okay, and it is a normal quasi-projective variety. Okay, so you can again do the same argument that I had before with Serre duality to show that this is actually not too artificial, and that actually I can think of the moduli space, the cotangent space of the normal moduli space of parabolic bundles. This I can view as an open subvariety in the moduli space of parabolic Higgs bundles. Okay, and for genus greater than or equal to 3, the complement of, so if I look at the complement of the cotangent space in the space of the Higgs for this parabolic bundles, this has codimension at least 2. Okay, and why did I just put this result here? Because actually this result is quite key. For, you see, this says that this is for genus G greater than or equal to 3. Yeah, this is quite important. I will come back to this. Okay, so again, we also have the Hitchin map just as before. What do? I take my my bundle, I have the parabolic Higgs field this time, not just the Higgs field. And again, I look at the coefficients, yes, of the characteristic polynomial. Okay, so I can also define the Hitchin map. Okay, so there is a couple more ingredients I need to define, and that is that you see in this thing. So this has a name, by the way, this direct sum of these sections. It's called the Hitchin base. Okay, so here now if I take a tuple, let's say A2, A3, AR, I can consider the curve corresponding to this point A in the total space of the canonical bundle twisted with S. Okay, so that is a bundle. That is a bundle over my curve. I can look at its total space, and there I can look at the curve which is defined by this equation. Yes? Okay. Now, what happens is that this curve has a name. It's called the spectral curve. And in some cases, which I think Thiago will probably talk about on Friday, he's nodding, this happens to be smooth, and in some cases, it happens to be singular. Okay? So I denote by D the set containing the points in here such that the corresponding spectral curve is singular. Okay? And this is called the locus of singular curves, singular spectral curves to be more precise. Okay? And it's, so we had the Hitchin map, and its pre-image in the Hitchin map is called the Hitchin discriminant. Okay. So finally, I can tell you, how do they prove these Torelli type theorems? What was there in the result of Alfaya Gomez? What is there in the result of Luana and Thiago? What is there in general when they're trying to do these Torelli type theorems for parabolic bundles? What we try to do, or what they try to do, is that you try to retrieve the curve from the dual of the projectivization of this locus of singular spectral curves. Yes? And to make it more precise, so what happens is that you start off with, let's say, what do you want to show? You want to show that if I have this morphism between two moduli spaces of parabolic bundles, I actually will get an isomorphism between the curves. Yes? So if I had the isomorphism between the curves, of course, there'd be an isomorphism between their moduli space of parabolic bundles. I'm trying to get the curve back from the moduli space of parabolic bundles. So let's start with the moduli space of parabolic bundles for both these curves, okay? And suppose I have this, and this should say that this is an isomorphism. Then what happens is that I can, of course, that will induce a morphism on the level of cotangent spaces. So I have that, okay, just from phi again. And then for each of these cotangent space, I have this Hitchin map. Yes? Just told you that. In the cases of genus G greater than or equal to 3, when I have this result about the codimension, yes? So that means that the complement of the codimension of this, the complement of, was it so bad? I guess I continue. So the complement of this in the moduli space of Higgs bundles, as I just showed you in the previous slide, that has codimension at least 2. So you can use that fact to actually show that there is going to be a morphism here, zeta, which kind of maps the singular locus, that D here, to the D here. Okay? And then you want to say that actually, I mean, this is not easy to show. I'm giving you the fairy tale version. You want to say that if I take the dual of that D and its projectivization, I can actually get back the curve. So that's how you conclude the proof. So yeah, it's very quick, but I don't have too much time to actually go on and give you all the details. Already, I think this is quite a lot of notation and definitions, but hopefully this gives some idea. Okay, now for small genus, the problem is the existence of this zeta. Okay, this is what we don't have. So in the result of Thiago, I can't see now, it's a bit dark, what happens is that he shows that this map does exist for genus 1, rank 2. Okay, so this zeta is somewhat, as I said, it follows from this dimension of from the argument of the codimension. For g greater than or equal to 3, this is already kind of given by Faltings. But for lower genus, this is not clear. So Thiago shows that this for g equals 1, rank equals 2, this still exists, and it does what you want it to do, which is to take the locus of singular spectral curves to the locus of singular spectral curves, and then you can get back your curve from that locus. Okay. Right, so the only problem with this darkness is that I'm no longer able to tell the time.
But you're good, you still have 20 minutes.
20 minutes?
Yes.
Okay, I wanted a bit more, so I might have to...
Okay, I give you 21.
So generous, so typical of George. So, okay. Okay, so the question is, as I said, it was the first time I came across these kind of arguments, I was not very clear what was going on. It seemed like there is a machinery that people are already aware of, and then they just put everything in that machinery, go through the motions, and they get the result. Yes, all this singular spectral curve business, all this discriminant business, it seemed very, I don't know, it didn't seem very clear. Why are you looking there? Why not somewhere else? How do you know this is the place to look at? I wouldn't know immediately if you asked me this question that this is the place to look at. So, but apparently it's not as ad hoc. I mean, there is a very nice reason why people look at this, and it just means that I need to read more. So one of the reasons for why people look at this is that these things are actually very well established by abelian-Hodge theory. So let me state some. Again, I'll be a little bit fast here because I'm running a little bit out of time, and also, yeah, this is probably stuff that people kind of know. So if you take X to be a smooth complex algebraic variety, there are various cohomology theories that you can associate to this. Yes. So the one that we learned the first time we come across cohomology is the singular Betti cohomology. And then after some time, we learn a little bit about the de Rham cohomology. And there is a theorem by de Rham which tells us that the cohomology ring, the Betti cohomology ring, is isomorphic to the de Rham cohomology ring. Okay? And then you can also think of the Dolbeault cohomology, which is that you just basically look at this direct sum of these, so basically sheaf cohomology, yes? So we are looking at the sheaf of differentials. And then Hodge's theorem tells you that you can go from de Rham cohomology to Dolbeault cohomology, okay? And when you put this together, all of this, what you say is that actually, since Betti is going to de Rham and then de Rham is going to Dolbeault, what this means is that I can write the cohomology ring of, or any Betti cohomology in terms of the Dolbeault cohomology. Yes? Okay. I.e. sheaf cohomology, and this is the Hodge decomposition. Okay. So what happens is that you can, in order to prove Torelli type results, so I'm just talking normal things here, yes? So far I haven't gone to vector bundles. What we can do is we can identify H1 Betti, yes, of C star with the space of homomorphisms, where pi1x is the fundamental group. We can identify the space of the de Rham space with algebraic local systems. And what the previous theorems tell us is that we have that the H1 can be decomposed as this, yes? So this is, sorry. So H1 dol is the pairs of holomorphic line bundles and a holomorphic one form. And by de Rham and Hodge's theorems, we have that the Betti cohomology is isomorphic to the de Rham cohomology, is isomorphic to the Dolbeau cohomology. Okay? So all of this, as you know, should know, is that C star is abelian. Yes? So non-abelian Hodge theory asks is that if instead of looking at coefficients in something abelian, C star, what if I was to look at exactly these theories, but with coefficients in some reductive group G? Okay? And then I can try to see if, when I look at the reductive group GL1C, I get C star and I get these back. Okay? So non-abelian Hodge theory is basically just doing that. So here what you do, so I'm going to go a little bit fast, and as this is not really part of the part of what I'm going to say next. It's just a kind of why did people look at all this cotangent space and know that this is the right thing to look at. Okay? So in non-abelian Hodge theory, you know that if you look at the if you look at the Betti cohomology now, this is the affine quotient of the affine variety, which is the homomorphisms of so representations of the fundamental group. Okay, modulo some things. So this is called the character variety, and you can think of the Betti cohomology for non-abelian. So for some arbitrary reductive group, as you can think of that as being the moduli space of flat GLNC connections. And the Dolbeau, in this case, can be identified as the moduli space of semi-stable rank n degree 0 Higgs bundles. Okay, so of course, if you want degree not 0, you can, there are also versions of these things, and they're smooth moduli spaces when rank and degree are co-prime. So for example, you can think of the Betti, yes, as just C star to the power 2G. Higgs is just going to be the cotangent space of the Jacobian, and the de Rham is a certain affine bundle. Okay, so this is really not as unnatural as it first looks. And the idea is that in the non-abelian setting, the Riemann-Hilbert correspondence gives you the equivalent of de Rham's theorem, and the Hodge's theorem is given by this result by Corlett and Simpson, Corlett in rank 2 and Simpson in general case. Okay? And then similar correspondences exist in the parabolic setting. So, okay, so my point here was that although this looked very, when you think of it in terms of the Higgs bundle being the Dolbeau and you have this de Rham and Betti, then it does not seem so random because you have already these isomorphisms, these correspondences. I won't go into detail whether these are analytic or not, but it doesn't seem so random that you actually switch to the theory of Higgs bundles. Okay? So I don't know if that helps much, but it was a very quick thing. So this is why people all of a sudden, when they're trying to prove these results, they try to look at the cotangent bundle. Let's say you're trying to prove something, yes, for the Jacobian. And then they try to look at the cotangent bundle, and then you try to think, oh, but you know, I could think of this as in terms of Higgs bundles, and so there you have this Hitchin map. So first time round it looks very random, but it's not. Okay, at least that's what I felt. All right. So as I tried to stress, but the lights had gone off, is that this is kind of this methodology. Yes, this is hard to do for genus 1 arbitrary rank. Okay? So in low genus, you don't have this zeta, and then for some ranks, you might still be able to get it, but not in general. Okay, so what can we do for our case when we are interested in rank 3, genus 1? So far, are there any questions? No. Okay, very good. All right. So hopefully everybody is happy with. Oh Lord, I'm terrible with this. All right. Okay. So let's recall what was rank 3 1 point. Rank 3 1 point means that I'm just looking at these parabolic bundles, okay? And I have this filtration, and I have these weights, and then in this case, what I have is that a parabolic subbundle is going to be of rank 1 or 2, okay? So the goal was to try to get the, look at the moduli space of these bundles, okay, semi-stable, and then ask, let's even make the determinant to be trivial, and then see if we can get back the curve from this. This was our goal. So clearly, the strategy that we have from Passarella, Justo doesn't work, okay, or the general strategy of Alfaya Gomez, et cetera, doesn't work. So what can we do? We still attempt the goal, and we do the following. We do something more hands-on, okay? Instead of going into all this non-abelian Hodge and looking at these correspondences and then trying to get all this spectral curve business and the locus of singular spectral curves and all this stuff, it's great, but it's not going to work here. So let's do something a little bit more hands-on. So what we do is actually related to the strategy of Nestor Fernandez Vargas. So I mentioned that in the beginning, and I said I'll come back to it later. So our strategy is very similar to his. So what he does is that none of this Higgs bundle stuff, yes? Get your hands dirty, do it more hands-on, try to actually understand, but in his case, it's 2 points, and it's rank 2. And he tries to understand what are going to be all the semi-stable parabolic bundles. Okay, so really try to understand the moduli space in a more hands-on way. And so we would like to do something similar here, but it's rank 3. It's harder because our subbundles are not just line bundles anymore. Okay, so there is definitely a bit more work to do. And some things that are maybe available to him are not quite available to us. So, but we try nonetheless. So the first thing we want to do is that we want to consider all possible weights. So we worked out the wall chamber decomposition. Okay, so how does the moduli space change as we change the weights? So what we know is so far, or you should have appreciated so far, is that the space of weights, yes, this is sitting inside some 0, 1, yes, in this interval for different dimensions. So in rank 3, this is going to be a cube. Okay, so it is sitting inside here, but we don't know what it really looks like. So that's one thing. And then the question is, what are the possible semi-stable parabolic bundles in each of the moduli spaces? So if you look at this wall chamber decomposition, for each chamber, you are going to know that all the moduli spaces are going to be isomorphic. So take a moduli space in there and then ask, what are the bundles that are going to be semi-stable with respect to the weights here? Okay? And there will be some bundles that are going to be stable always. You know? So they're going to be stable irrespective of the weights almost. So what are those bundles? And then the question is, okay, so maybe the bundles, so I'm just explaining the strategy very briefly, in case I run out of time, which might happen. So the question then is that can I retrieve the curve from the locus of the bundles that are not common to all the moduli spaces? Yes? So the ones that are not always stable for any chamber. Okay, so as I said, by definition, the weights are sitting inside here. Yes? But we can translate the weights by a constant, and therefore they need not be between 0 and 1. Just the difference between the largest and the smallest needs to be 1. And if we do that, it does not affect the parabolic stability condition. Okay? So for our intent and purposes, we can just assume that the sum of the weights is 0. And actually, we found that in an article by Cézanne, I will not be able to pronounce this correctly, so I'm sorry. Andras Cézanne and Olga Trapeznikova, the weights, mu I, that satisfy these conditions actually are a triangle. Okay? So can everybody see? Anyways, just a triangle. and it's going to have 2 regions. Okay? So one is going to be labeled P0 greater, the other P0 less. And so the conditions here is that this is what greater and less than means is for mu2 in the weights to be greater than 0 or less than. Okay? Okay, so this was this we found, and they say exactly, they're exactly in our setup. And then the question is for us to really find out what are the bundles that are stable with respect to the weights in P0 greater and P0 less. Yeah? So normally, semi-stability, as in vector bundle semi-stability, does not imply parabolic semi-stability, or vice versa. Okay? If the weights are very, very small, then Yokogawa shows that it's going to be the same, but that's kind of easy to say. If the weights are 0, then of course that's true. But in general, this is not going to be the case. However, if you just have one point, so a unique parabolic point, parabolic semi-stability does imply usual vector semi-stability. So what that means is that so that means that if it is not vector bundle semi-stable, as in usual semi-stable, then it can't be parabolic semi-stable. Yeah? So if we want to look at parabolic semi-stable things, we should just consider those that are usual semi-stable. And that's what we do. So there is a classification by Atiyah of the vector bundles of any rank on an elliptic curve. So we use the classification for rank 3, okay, trivial determinant, and this is what we find. So we know that our bundle is going to be one of these 3 types. Okay? So it's either going to be the sum of 3 line bundles, where Li, Lj are in the Jacobian, and then that kind of, because we have trivial determinant, that determines the third one. Or it's going to be E2, the indecomposable bundle, Atiyah's indecomposable bundle of rank 2, tensored with L, direct sum L to the minus 2. Yeah? Or it's going to be the indecomposable bundle of rank 3, tensored with a 3 torsion line bundle. So this is given by Atiyah, Atiyah's classification. So we know that since we need our vector bundle to be semi-stable, it is going to be one of these 3. Okay. So the question then is that how does it work for the different chambers? So this is what happens. So I told you earlier that you can write the parabolic stability condition in this form, and it's a bit easier to work with. So what we find is that what's the big difference between parabolic stability and the usual stability? The thing is that you're not just considering a subbundle anymore, right, in order to show that something is stable or not. You also have to consider the flag and the position of the flag, because the position of the flag is what's going to determine the weights. And that determines the parabolic degree and whether or not it is going to be stable or not. Yeah? So this is precisely what we do. So for each of these, for the weights here, so we look at what are the things that are going to be, let's say, semi-stable with respect to something here, okay, and what are the things that are going to be semi-stable with respect to something there. But more importantly, we see what are the things that are going to become destabilized. Okay, so for example, if I look at my bundle L1, L2, L3, okay, and I can show that this is going to be parabolic semi-stable for one of the chambers, but not for the other, if I ask the flag to be this. Okay? Because that is going to determine whether or not I can take a subbundle which violates the stability. Okay, so the parabolic degree of Lj is mu2, parabolic degree of E is 0. So E is semi-stable in the chamber where mu2 is less than 0, but unstable in the chamber where mu2 is greater than 0. Okay? So it's the you can take exactly the same bundle, but then the flag will determine whether or not it is stable or not. Okay, and then on the other hand, since I'm running out of time, I have bundles that are always going to be stable. So this is the kind of bundle. So I wanted to draw this picture because Frank really likes these. Okay, is that you can think of, so here, what am I doing? What is this picture? So I am looking at E, P, okay, projectivized. So E is of rank 3, so I projectivize, I get something flat, okay? And what I want to think of is that suppose that this is L1, this is L2, this is L3, okay? So my pictures are quite bad, so I always hesitate to draw them. But the thing is that if I ask my flag, so this is E2, okay, and maybe I should have drawn that in color, but never mind. And this is E3. So if I have this to be the flag, maybe, yeah, which is not intersecting any of the projectivizations of the line bundles involved, then this is always going to be stable for both the chambers, regardless of which chamber I'm in. Okay? So that means that essentially the two moduli spaces that I get, right? So let's say for here I get M0, and for any point here I get M0 plus, or vice versa, maybe minus and plus, yeah? What's going on is that both of these moduli spaces are going to contain the set of generic bundles, okay? And the generic bundles are those that are always stable. Okay, but the question is, what else do they contain? So that is what we need to understand. So this is work in progress right now, and I'm not going to say too much about it, especially because I'm running out of time. But essentially, we want to understand that this does have Eugen, yes, but it also has something more. So Eugen and plus compactification locus, yeah? And then this one also has Eugen and then compactification locus plus. So what is in this compactification locus plus and what is in the compactification locus minus? This is what we are right now trying to understand. And Frank is confident that this compactification locus is going to give us back the curve. Okay? So if you're thinking I'm just waving my hand, there isn't a clear strategy, ask the birthday boy. It's not me. Okay? He's confident. So thank you for your attention.